Okay, welcome back. Now we are gonna start chapter 5 as I promised, which is about angle modulation. So let's see how the discussion goes for angle modulation. So up to now in amplitude modulation, what we have seen is the signal's amplitude, the cosines or the sinusoidal signals amplitude was changed by the message or by the message signal that we are going to send. But now in angle modulation, what we are going to do is change the frequency or the phase of the sinusoid, the carrier sinusoid, due to the message signal. Okay, so let's see how it goes. So in AM, what we do is mt times cosine omega ct. So the information is at the amplitude. Amplitude is changed with the message m of t. Now the idea in FM, the frequency modulation, is what if we change the frequency or the phase of the signal instead of the amplitude using m of t. So so the idea is in frequency modulation, for example, what you will send is an a cosine. So you will change your omega c plus, for example, kf times m of t, okay, times t, okay. So now what you are doing is you're changing the frequency here. Omega c is the original frequency, and making it proportional to kf times m of t, okay. But before delving into more discussion about this, I'm going to introduce a more generalized form of a sinusoidal signal. So up to now what we have seen is a sinusoidal signal that looks like this, right? A cosine omega ct plus theta, okay? So this is a sinusoidal signal, right? Now, okay, yeah, this is a sinusoidal signal, but can we generalize it? Can we generalize such that it has more elements in it? Because now let's see, I'm gonna define let phi of t equal to a cosine theta of t. So I'm gonna define a generalized sinusoid, if you wish, generalized signal. Okay, of course the regular sinusoidal signal is a kind of this generalized sinusoidal signal, because I can write for conventional sinusoid, I can write theta t is equal to, right? So I can write theta t is equal to omega ct plus theta. So it covers this notation that I use, that I introduce here, covers the conventional sinusoidal signals, but it is more general, okay? And then using this general notation, we are going to describe phase modulation and frequency modulation. Before that, we need to describe one more thing, the instantaneous frequency. So if you think about this, if you think about theta t, now for a conventional sinusoid, theta t is a line, omega ct plus theta is a line, but in general it can be anything. So let's say it's just a function that looks like this, maybe. For at a certain time, what is, if somebody asks you at a certain time, what is the frequency of this sinusoid kind or generalized sinusoid? What is the frequency of this generalized sinusoid at this time, t0, for example? How would you find it? How you would find it is by taking the derivative. Basically, you need to find the tangent, the derivative here, and the slope of this tangent is going to be your instantaneous frequency. So I'm going to define W instantaneous t as the derivative of the generalized phase. So yeah, I can call this theta of t as the generalized phase, right? So this is the generalized sinusoidal signal, and theta of t is the generalized phase. And now in this case, if I look at it this way, the instantaneous frequency will be the derivative of this phase. Of course, for the conventional sinusoid, it will be equal to omega c, which is the carrier frequency. And from this definition, I can immediately see that theta of t I can obtain by integrating the instantaneous frequencies. Wi of alpha d alpha. Okay, this comes from, again, fundamental theorem of algebra, calculus, which is not algebra, sorry. So the fundamental theorem of calculus, which is if one signal is a derivative of the other one can be obtained from the other signal by integration. Okay. So now given this, with this tool of generalized phase, I can define a phase modulation and the frequency modulation. Okay. So let me define first the phase modulation. Okay, so in phase modulation, what we do is we will change the generalized phase of a carrier signal by adding so I'm going to define theta t of the phase modulated signal as original carrier's phase, which is omega c times t. So this is my just carrier phase, plus I'm going to assume there is no phase here, although there may be, kp times m of t. Okay, so I'm going to change the phase in proportion with the message signal. Okay, and this kp is called the phase sensitivity. Phase sensitivity of the modulator. Okay. Alright, so what does the signal look like then? A phase modulated signal will look like, it has an amplitude and a cosine omega ct plus kp m of t. So I'm changing the phase here. So what would be the instantaneous frequency in this case? So Wi would be just the derivative as the definition. The instantaneous frequency is going to be omega c plus kp m dot of t. So here m dot is the derivative of message signal. Okay, so that is the instantaneous frequency of the phase modulated signal. In frequency modulation, so phase modulation shorthand is PM, and for frequency modulation the shorthand is FM. So in this case, what I'm going to change is the instantaneous frequency Wi of t, which is going to be omega c plus kf m of t. Sorry, omega I of t. It's not W, it's omega. Well, okay, so it now here in this case the instantaneous frequency is changing linearly with m of t. Is changing linearly with m of t. Okay. Okay, so okay, I'm gonna come back here and I'm gonna say that this was wrong. Okay, not true. Okay, so we'll see why now, because you need to do instantaneous frequency, so it's not really instantaneous frequency if you define it this way. So I'm gonna show you how the phase is going to change if you do this. The theta at t is going to be minus infinity to t omega c plus kf m of t d alpha. So yeah, my t is my integrations upper range, so I'm gonna use a different letter, alpha. So this is gonna be the theta of t. So if you do this thing, what you get is omega c t plus kf times integral minus infinity to t m of alpha d alpha. Okay, so this is what you get actually. So this is your signal. So what I wrote above was wrong. So phi fm of t is basically a cosine omega c t plus kf integral from minus infinity to t m of alpha d alpha. Okay, so compare it what I had written here. It's not true. Okay, so you cannot really do this. You cannot really assume that this would be the same. And under some certain circumstances this could be true, but basically when mt is constant this would be true. Mt is constant over it. Yeah, if mt is constant this would be true. Otherwise it's not true. Okay, so this is the correct one. So this is the correct FM signal. Okay, because you need to change the instantaneous frequency being proportional to m of t. And since you are instantaneously changing the frequency, the cumulative effect will be this integral. Okay. Okay. So let's see. So I hope you all see the differences between FM and PM. In PM, this is the signal we get. Okay. In FM, this is the signal we get. Okay. All right. But how are these related? Are these related? Can I obtain one from the other? So let's see how they are related. So the generalized concept of angle modulation. So so it's maybe easy to see that they are very similar, right? So what is the difference? Here I'm adding kp times m of t as an argument to my cosine, and here I'm adding kf times the integral of m into my cosine. So I can see that the FM wave for m of t is the same as the PM wave for the integral, for this integral m of alpha d alpha from minus infinity to t. So there is such a relation. So it may not be possible to tell the difference. For example, if your message is a cosine omega mt, which is like the pure tone, then your integral will be a sine omega mt, right? Or yeah, plus minus the sine. So what you will do, it's hard to tell them apart actually. So we can see that if you take m of t and then pass it through this integrator, okay, and then do phase modulation with a carrier signal, you would get the signal FM, original FM signal, as you can see here up in this equation for FM. And similarly, if you take m of t, pass it through a differentiator, and then apply frequency modulation to the end, what you get is the phase modulated carrier signal. Okay, but yeah, this would be like indirectly getting what you want. Okay. So again, in general, if you want to combine these two, we can define. We see that these two are linear time invariant systems, the integrator and the differentiator. I can define an angle modulation. generalized angle modulation, phi of t as a cosine omega ct plus the output of a system. So I'm gonna put m of alpha, h of t minus alpha, d alpha. So this is the convolution, right? So I'm convolving mt with an h of t here. So this is mt convolution h of t. Okay, what is h of t? So if your h of t is a differentiator, sorry, if your h of t is a delta t, okay, kp times delta t, then you get phase modulation. If your h of t is kf times u of t, which is the unit step, now you're passing it through an integrator, right? So in this case, what you're doing is you're doing this star here, okay? It's the same as star. So what you're doing is you're passing your m of t through an integrator. And what is the impulse response of an integrator? It is u of t. And if your system here is just nothing, then you get the phase modulator, okay? And this is how you can generalize the angle modulation scheme. Now let's do an example and see what is really happening in the time domain. Let's consider such a signal m of t that looks like a triangle, okay? This is an example from the book. So what we have is it goes from plus 20,000 to minus 20,000. Okay, so that's the signal. Wait, let me see. Just make sure that this is the case. And that's the period, sorry. So the period is 2 times 10 to the minus 4. So it goes from 1 to minus 1. And the period is, so it goes like this, periodic. Okay, it's a periodic triangle signal. And the period is 2 times 10 to the minus 4. Okay. Now let's see, and I'm gonna define a kf and kp. And kf, this is the frequency sensitivity, is 2 pi times 10 to the 5. Okay. And kp is equal to 10 pi. Okay, so this is given. And the central frequency of the modulated signal is gonna be, okay, my one node is restarting. I hope it will restart soon. I can stop here and then we'll continue. Oh no, okay, I don't need to stop. Okay, I will continue. Okay, so let's write down what was those numbers. So kf was 2 pi 10 to the 5. kp was 10 pi, and the carrier frequency is 100 megahertz. Okay, so I'm gonna use a very high frequency carrier to modulate the signal. I'm gonna use this m of t to modulate the carrier, of course, right, by changing its frequency. Now, okay, so in frequency modulation, so let's consider FM first. So I'm gonna write the instantaneous frequency f sub I as f sub c plus kf divided by 2 pi m of t, right? So this would be my instantaneous frequency. Now m of t goes from -1 to 1, so the largest value is -1. So my minimum instantaneous frequency is going to be fc minus kf over 2 pi, and my maximum instantaneous frequency is going to be fc plus kf over 2 pi, because the maximum and minimum values of m of t is maximum m of t is equal to 1 and minimum m of t is equal to -1. That's why I'm gonna keep changing between these two frequencies. And what are these frequencies? This turns out to be 99.9 megahertz by if you plug in these numbers, and this turns out to be 100.1 megahertz. Okay. How about in phase modulation? Now in phase modulation, my instantaneous frequency is going to be the carrier frequency plus kp over 2 pi. Now m dot of t. Okay. My m dot of t, what is the minimum and maximum values of my m dot? My m dot is the derivative. So what is the derivative of this signal here? So if you consider this triangular signal, well, it is basically here. It's gonna turn out to be 10 to the 5. Okay. Because it's the slope. How would you find the slope? It is 2 divided by 2 times 10 to the -4. Let me see. It must be 1 times. Okay. So let's see. What is the m dot? So I'm gonna plot the m dot function. Okay. How is the m dot function changing? So it's gonna be negative first because there's a slope is negative initially, and then after a while it's gonna be positive, and it's gonna be negative again. And what is the numbers there? It goes from minus 20,000 to 20,000. Okay. Okay, so it's such a signal, the m dot. So, and kp is given as 10 pi, so what you get is f sub I minimum is gonna be fc minus kp over 2 pi times 20,000, and f sub I maximum fc minus plus kp over 2 pi times 20,000. Okay. And if you do this, kp was given to be 10 pi, so this is 5. So this is get 10 to the 8 minus 10 to the 5, which is equal to 99.9 megahertz again. And this is similarly 100.1 megahertz. Okay. But are these signals going to be the same? I mean the FM and the PM signal? Well, the answer is no, right? It's because they will be modulated differently. How is it going to be different? In PM, what will happen is that you will have a, let's plot the phi PM. Okay, let's try. At least it's very difficult, but yeah. So here initially in this period, in the first period from 0 to 1, okay, that's the time. No, sorry. 0 to 2 times 10 to the -4, sorry, 10 to the -4 here, and this is 2 times 10 to the -4. Okay. What will happen is that you will have a carrier frequency which is the smallest, which is 99.9 here. So you'll have a frequency here which is gonna be 99.9, and then after that you will have a larger frequency. It's impossible for me to draw it here actually. So it's gonna be higher frequency here. It's very hard to draw it because there's very little difference. It may be even very hard to see with your eye, this difference. But anyway, so this region will be high frequency, and then there will be another region with low frequency. And the amplitude is not changing actually, so my plot is wrong here. So what you will see is the amplitude is always A, between A and minus A, right? So this is A times cosine, well, 2 pi fct. What is the signal I'm plotting? It's 2 pi fct plus kp m of t. So this is what I am plotting here. Okay, so if you plot this signal, you will see that the only thing that's changing is the frequency. The amplitude is not changing. So amplitude is always constant, which is very much different than what's happening in amplitude modulation. How about in the phase modulated signal? In this case, in the first one here, FM. Well, in FM, what will happen is that since you have this triangular wave here, the instantaneous change there will be an instantaneous change in frequency. So there will not be regions like this. So in this one there will be regions: 99.9 frequency, 100.1 frequency, 99.9 frequency. How about in the FM signal? Now this is going to be a cosine 2 pi fct plus kf m. Okay, so this is going to be the integral, right? So kf times the integral minus infinity to t of m of alpha d alpha. Okay, so in this case, how is it going to be? Well, the frequency will change instantaneously. So initially it will be high. From 100.1 it will go down to 99.9, but gradually it will go. So instantaneous frequency will go down. Not sure if I can plot this, but yeah, the frequency will get smaller a little bit, and then it will be smallest, and then it will again try to raise the frequency again, and then it will again decrease the frequency, and so on. So the frequency here, f instantaneous, at this point will be 100.1, but here it will be the lowest. So at this point it will be the lowest, 99.9. Well, let me just say here 99.9, and then it will go up to 100.1. Will go down to 99.9, etc. So there will be like such a cycle going on, but here in the middle, what would be the instantaneous frequency? It will be something like 100. So it will be gradually changing from 100.1 to 99.9 in frequency modulation. Again, this one, the amplitude is constant. Okay, so you have A minus A, so everything is constant, the amplitude. Only thing that's changing is the frequency, but the frequency is changing gradually because of the nature of this m of t, as you can see here. Okay, I hope this is clear to all of you. Now, after this example, let's consider another example where the m of t is not continuous. So let's consider this example when m of t is not continuous. What will happen into the phase modulated signal? So if our m of t is like the square wave, so if it is like 1 here and then minus 1 here and then periodically like this, okay, 1 minus 1, 1 minus 1, like that. Okay, in this case the FM, let's do the FM first. So this is my m of t. So in FM frequency modulation, the instantaneous frequency is going to be again f carrier plus kf divided by 2 pi times m of t, right? So this is what you get for the FM, right? Same formula. So what will happen is that, let's say the carrier frequency is again 100 megahertz again. So again fc is equal to 100 megahertz. And what else? Let me see. Yeah, okay, so that's it. So in this case, kf is given to be, I'm gonna write down again, same, 2 pi 10 to the 5. So kf is again 2 pi times 10 to the 5, and kp is again the same. No, in this case kp is gonna be pi over 2. Okay, so if you consider this, what is gonna be the maximum and the minimum? Well, m of t goes between 1 and minus 1, so the maximum is gonna be when m of t is 1. So it's gonna be between so fi maximum is going to be 100 megahertz plus kf times, which is 10 to the 5 times 1, right? So again, this is 100.1 megahertz. The maximum, and the instantaneous frequency minimum is gonna be similarly 99.9 megahertz. Okay, how about PM? How is gonna be the phase modulation look like? Now if you go to this formula here, what we need to do for PM is we need to take the derivative, right? But now the derivative of this square wave is gonna involve deltas. So in this case, m dot of t will have delta functions. So do not use above formula, but use the direct thing, which is the following. Because the delta is we don't know. I mean, what will happen with delta, right? So we just use the direct, approach. Just write down what is going to be the function. The phi pm of t is going to be cosine omega ct, or 2 pi f ct if you want. We like to work with f's. 2 pi f ct plus kp m of t, right? So now you don't have to take the derivative at this point, because you are not talking about instantaneous frequency now. We are talking about the whole signal, and now we can see what happens. Okay, hopefully. So what will happen in this case is that this is gonna be equal to okay, kp was equal to pi over 2, remember? So now this is plus pi over 2 cosine 2 pi fct plus pi over 2 when m of t is equal to 1, yeah, and then cosine 2 pi fct minus pi over 2 when mt is equal to minus 1. Okay, so what's happening? Well, this is minus, well, yeah, there's an a, okay, amplitude, let's keep the amplitude. So this is going to be minus a sine 2 pi fct, and this is going to be a sine 2 pi fct. So it's not difficult to see what's happening. So how will this look like if you plot this phi pm of t? This is as if you are changing, you are not changing the frequency, but you're changing the sign of the thing at certain change points, like this. So what's happening is that you get a sinusoid, and at this point, after this point, if you continue a sine, it will continue like this, right? So it will continue like this, but instead of that, you continue with a negative, so you continue like this. Similarly, at this change point, you will continue like this, whatever. Okay, so this is how this modulation, the phase modulation, is gonna look like in this case when you have a discontinuous m of t. Again, you're changing between a and minus a. You have these abrupt phase changes, which affects how the signal looks in this case. So there's instant phase discontinuities happening. So at these points, instant phase discontinuity. Okay, I hope this is clear. Now we understand what's happening when we do frequency modulation and phase modulation, hopefully. And this continuity amount is Kp times the value of m here. The amount of discontinuity is equal to Kp times, well, should I say delta m, because the change in m, right? So delta m. So here Kp was pi over 2, and delta m is how much changes is pi. It's 2. So it's a phase change of pi between these two signals. Okay. Okay. One thing maybe I should say is about the phase. There's an ambiguity about phase, right? Yeah, so you should be a little bit careful about this point, that the phase, actually, the phase of a sinusoid, there's the ambiguity with okay, let's consider this. Cosine theta is always equal to cosine theta plus 2 pi. So there's this ambiguity of 2 pi, and it's actually even powers of 2 pi. So I'm gonna write here 2 pi k. So k is integer. So when k is an integer, there is this ambiguity. So you cannot really differentiate two angles that are 2 pi apart from each other, or multiples of 2 pi apart from each other. So this point is important. You should be careful about this point when you're drawing things or when you're thinking about the phase. So there is so we can map all phases to the range, to the principal range. Okay, there's something called principal range of minus pi and pi, where minus pi to pi. Well, minus pi and pi are also the same. So cosine minus pi is equal to cosine of pi. So if you think around the unit circle, like, so these are the angles, complex number, right? So here, so this is the theta, right? So if you rotate this 2 pi, you get onto the same point. This is the angle pi, and also minus pi, same. So this point is pi over 2 angle. This point will have a pi over 2 angle, and this point is minus pi over 2 angle, and this is the 0 angle. Okay, so just if you think from this complex plane on unit circle on the complex plane, it's easier to visualize things. And the cosine is basically, cosine of this angle is basically this direction, right? This length divided by the hypotenuse, right? Which is always 1 unit circle, right? So I'm considering a circle of radius 1. So the cosine, you can always think about that length, and sine is this length. Okay, cosine theta, sine theta. So here you can immediately see what is cosine 0, what is cosine pi over 2. Well, you will see that the cosine pi over 2 is 0 here, and cosine pi is minus 1. Okay. So we can work in this principal range of minus pi to pi of these phase angles, and we should be a bit careful about this. Okay, some certain times. Okay, so let's take a break now. I'm gonna stop for a while, and we'll see.